much, and also thanks for having me in this session. So this is about joint work with Florian Brandl, who's somewhere in the audience, and Georg Seedig. So what I'm going to do in this talk is that I'm reporting on some recent results of ours where we take classic impossibility theorems from social choice theory and then turn them into complete characterizations of an attractive probabilistic social choice function called maximal lotteries. So the idea is a little bit that just like major results in game theory require the existence of randomized strategies, randomization also allows for much more positive results in social choice theory, which is otherwise known for its abundance of negative results. So for example, if you have a look at the following table here, which is based on a recent paper by Dan Felsenthal, a political scientist who sadly passed away earlier this year, you will see a comparison between 5 different common deterministic voting rules or social choice functions: plurality, border, Schulze, instant runoff, and plurality with runoff. And all of these social choice functions suffer from various voting paradoxes. So for instance, scoring rules like plurality and borders rule are known not to select a Condorcet winner, which is an alternative that beats every other alternative in pairwise majority comparisons. At the same time, the remaining 3 rules are known to suffer from the no-show paradox, which means that voters can be strictly better off by deliberately abstaining from an election. So as you can see, so even if you only require relatively mild conditions, there's always a trade-off that has to be made in social choice. Now, if you extend the space of social choice functions to the space of all probabilistic social choice functions, and at the same time you generalize appropriately the definitions of these paradoxes or the underlying axioms, you can get some positive results. So in fact, somewhat amazingly, maximal lotteries, which is the function that I'm going to talk about, doesn't suffer from any of the paradoxes in this table. So that doesn't mean that maximal lotteries is without flaws, so we will see one of the flaws on one of the next slides, but at least it shows that some of the major trade-offs that you face in deterministic social choice disappear once you allow for randomized strategies, which is quite nice. So what we've been doing over the past couple of years is that we have looked at classic impossibility theorems, and then we have taken the axioms used in these impossibility theorems, we generalized them to the probabilistic setting, and then we turned the negative results into complete characterizations of maximal lotteries. So we've done so for using for Arrow's impossibility theorem. Then there's also an impossibility, which is basically an incompatibility between 2 types of consistency conditions by Peyton-Young. And finally, there's also the no-show paradox by Hervé-Moulin, which says that every Condorcet consistent social choice function, which is a social choice function that returns a Condorcet winner whenever one exists, suffers from the no-show paradox. And in each of these cases, we've generalized the axioms to the probabilistic setting and got positive results, namely a unique characterization of maximal lotteries. So in this talk here, I'm going to focus on the consistency impossibility. So to make sure which kind of formal model we are using here, so a probabilistic social choice function is a function that takes as input a preference profile. So we have a finite number of alternatives and a finite number of voters who have ordinal preferences over these alternatives. And these are usually represented by a preference profile, just like the one that you can see here. So here we have 3 alternatives, A, B, C, and 3 voters. The first voter prefers A to B to C, the second one B to A to C, and so on. And now a probabilistic social choice function is mapping any such preference profile to a lottery over the alternatives. So in this case, for instance, it could be 2/3 A and 1/3 B. So I'm going to write lotteries as convex combinations of alternatives and sometimes also as vectors of probabilities whenever that's more convenient. What the function in this example does is exactly what random dictatorship would do. So that's maybe a probabilistic social choice function that many of you are familiar with. Random dictatorship just works by selecting one of the voters uniformly at random and then just taking whatever this voter's top choice is. And random dictatorship is well known in social choice because there's a characterization by Alan Gilbert from 1977 where he showed that it's the only probabilistic social choice function that satisfies strategy proofness and Pareto optimality. So hence, since maximal lotteries, which I'm going to define, satisfies Pareto optimality, it cannot satisfy strategy proofness, like any other deterministic social choice function, which is somewhat reasonable. So it turns out that strategy proofness is one of the conditions that still remains rather restrictive even in the probabilistic setting. That holds in particular for the relatively strong interpretation of strategy proofness that was used by Gilbert. So if I have some time in the end, I'm going to talk a little bit about strategy proofness. But otherwise, I'm going to use different conditions for our characterization, namely 2 conditions that have been used in social choice before. They are both consistency type conditions. The first one is consistency with respect to a variable electorate, and the second one is consistency with respect to components of similar alternatives. So the first one, which is called population consistency, is quite well known in social choice theory, and the definition is also rather simple. So it just says if you have two different electorates and the function applied to each of these electorates yields the same lottery, then we should also get the same lottery if we merge these two electorates into one. So for example, if you have an electorate like this one here consisting of two voters, and the outcome would, for instance, be 1/2 A and 1/2 B, and we have a second electorate where the resulting lottery is also 1/2 A plus 1/2 B, then if we merge these two electorates into an electorate of 4 different voters, then the outcome should still be 1/2 A plus 1/2 B. That is very straightforward. And this condition is famously used for the characterization of scoring rules in social choice theory. And in a slightly different context, it has also been used for the characterization of Kameni's rule. Now, the second axiom, composition consistency, is a bit less known in social choice theory, and I would say it's a bit underappreciated because it's mathematically actually very elegant. So here the idea is as follows. So whenever it's possible to decompose a preference profile into different components, then we should be able to apply the function to each of these components separately and then just merge these results in an appropriate way. So I'm going to show you what I mean by this. Let's say we consider the following preference profile here. So we have 3 alternatives again. And it's pretty obvious that 2 of the alternatives are very similar to each other. So they are similar to each other in terms of the preferences of the voters. So B and B prime, as you can tell from the names as well, are just clones of each other because they're adjacent in each of the preference relations by the voters. So whenever a subset of alternatives forms an interval in each of the preference rankings, we consider this to be a component. And now what you can do is you can just separate this preference profile into 2 different preference profiles. You can think of the, let's call it meta preference profile, if you just consider A and one of those clones, so just A and B, for instance, or A and B prime, it doesn't matter which one we take. And then we have a second preference profile, which is just the preferences over these 2 clones, B and B prime. And now what composition consistency says is that the outcome of the first preference profile should be completely determined by the choices in the 2 other preference profiles. So for instance, if in the meta profile, we would choose 1/2 A plus 1/2 B, which is also what random dictatorship would do. And in the second one, it would be 2/3 B plus 1/3 B prime. Then we can just combine these 2 results together. And in the probabilistic setting, that would mean that for the first preference profile, we would need to have 1/2 A plus 1/2. And now we're replacing B with the lottery that we get for the clone preference profile. That is 2/3 B plus 1/3 B prime. So if you just multiply this out, then we get 1/2 A plus 1/3 B and 1/6 B prime. That's what composition consistency is about. So this axiom was proposed by Lafont, Lallier, and Le Breton in the 90s, but there are a lot of precursors in both decision theory and also in social choice theory, which just handle with the cloning part of composition consistency. Okay, now that we have the 2 axioms, so those of you who are familiar with social choice theory will know that population consistency is essentially only satisfied by scoring rules in the deterministic setting. At the same time, Lallier has shown that scoring rules cannot satisfy composition consistency. So it turns out that these 2 properties are incompatible with each other in deterministic social choice. And what we have proven for the probabilistic setting is that there's actually only one probabilistic social choice function that satisfies both of these axioms, and that's maximal lotteries. The proof of the statement is rather involved, so it took us several years to get it right. And I'm brushing over lots of technical details here just in an attempt to state the theorem as simply as possible. So as a matter of fact, actually, probabilistic social choice functions may return more than one lottery in exceptional cases. We are also working with so-called fractional preference profiles in our model, and probabilistic social choice functions satisfy a number of technical conditions like upper hemi-continuity, for instance. So the proof uses a lot of geometry and linear algebra. So what I haven't shown you yet is a definition of maximal lotteries, so I saved this for the second part of the talk. So let's see how maximal lotteries are defined. First, the maximal lotteries have been first proposed by a Frenchman called Germain Crévarat in the 60s in a very hard-to-get paper. And then they were rediscovered by Fishburne in the 80s, and then rediscovered over and over again by economists, mathematicians, political scientists, and even computer scientists. So the last paper mentioned here is by Ron Rivest and Emily Shen, 2 computer scientists. Now, in order to define maximal lotteries, we need the notion of a majority margin matrix. So those of you familiar with social choice will have seen this many times. So it's a basic concept that is used in many definitions of social choice functions. So the idea of this matrix is just that for two alternatives, x and y, at row x and column y, we just write down the number of voters who prefer x to y minus the number of voters who prefer y to x. And once we have this matrix, the definition of maximal lotteries is rather straightforward, because a lottery P, which is now just a vector of probabilities, is maximal if and only if the transpose of P multiplied with the matrix M yields a row matrix which is non-negative. Okay, so PTM is greater or equal than 0. So if you think about this definition, this can be rewritten using so-called bilinear expected majority margins. You can say that PTMQ for any other lottery Q is greater or equal than 0, which essentially means, and that's where the name comes from, that a maximal lottery is at least as good as any other lottery if you compare these two lotteries to each other. So one way to phrase this, for instance, would be to say that the expected number of voters who prefer the outcome of P to the outcome of Q is at least as large as the expected number of voters who prefer the outcome of Q to that of P. So maximal lotteries are maximal in the sense that they're as good as any other lottery. And this, of course, really means that maximal lotteries are nothing but randomized Condorcet winners. And there's also an interesting connection to game theory, which you may have noticed if you have looked at the definitions carefully, because this matrix M is a skew-symmetric matrix, and you can just interpret it as a symmetric zero-sum game. And then maximal lotteries are just exactly the max-min strategies of that symmetric zero-sum game. It doesn't matter whether we look at the row or column player because the game is symmetric. So there's a very strong connection to game theory, which is quite useful. Let me show you some examples for maximal lotteries. So for instance, in this preference profile here, we have again 3 voters and 3 alternatives. And now if we construct this pairwise majority margin matrix, it turns out that there's a degenerate maximal lottery. And in that lottery, we put all probability on A and probability 0 on both B and C. And that can be seen by just observing that the first row of that matrix only contains non-negative entries. And if this matrix in one row only has non-negative entries, then the corresponding row is a Condorcet winner, right? Because that candidate, alternative A, wins against every other candidate in pairwise majority comparisons. And that always turns out to be the case. So whenever we have a Condorcet winner, a maximal lottery will put all probability on the Condorcet winner and 0 probability on the other alternatives, which is quite useful. However, the main source for all these negative results in social choice theory, including Arrow's theorem, is the non-existence of Condorcet winners. But the nice thing is, once we have randomization, of course, because it's just like max-min strategies, we always have existence. So for instance, in this profile here, which is just the classic Condorcet cycle, we again have 3 alternatives, but every alternative is majority dominated by some other alternative. Still, of course, we have a maximal lottery, which is to assign uniform probabilities to all the 3 alternatives, which is obvious because the game is exactly rock, paper, scissors, and we know that the only optimal strategy for that game is 1/3, 1/3, 1/3. So the main advantage of maximal lotteries is that they always exist because of the minimax theorem. Maybe you're also wondering about uniqueness, because obviously maximal lotteries, just like max-min strategies in those zero-sum games, don't have to be unique. So if there are majority ties between all the alternatives, then every lottery is a maximal lottery. But it can be shown that this is an exceptional case, and that in most cases, maximal lotteries are indeed unique, and there are some special subdomains where this is the case. For instance, if you have an odd number of voters, all of which have strict preferences, then there's always a unique maximal lottery for any preference profile. One nice advantage of maximal lotteries for practical purposes is that everything just depends on the pairwise majority margin matrix. And that means we don't require preferences to be strict. We can have ties in the preferences, which, for instance, is a problem for random dictatorship. We can also have cycles in the preferences. And that means in some applications where we have lots of alternatives, we can only require the voters to maybe rank some of them. They don't even need to take care to avoid any cycles, and then just submit this information. And then everything is added up for the pairwise majority margin matrix. And we can just compute maximal lotteries even without having complete transitive preferences from each of the voters. Then another advantage, of course, is that maximal lotteries can be computed efficiently. That's obvious because, well, max-min strategies in zero-sum games we can also compute efficiently. One other point that is possible, that is worth mentioning, is that there are some subdomains of social choice. You can think of social choice or the voting domain as the most general setting in preference aggregation, and then you can define subdomains that are considered with that deal with say hedonic games and matching and house allocation. And in the domains of matching and house allocation, maximal lotteries have been again reinvented, and they are called popular mixed matchings in these cases, which is also quite interesting. So we are still working on maximal lotteries, and there are a couple of other results that we obtained that I didn't have time to go into detail here. Maybe just 3 of them that I would like to mention at the end of this presentation. So first I mentioned that maximal lotteries do not satisfy strategy proofness, but you can define weaker notions of strategy proofness. So the notion of strategy proofness that is used in Gilbert's theorem is essentially stochastic dominant strategy proofness, and also a strong version of that. And we have defined weaker notions of strategy proofness where the voters are actually only able to compare some subsets of lotteries to each other, and in many other cases they will have incomparabilities between 2 different lotteries because there's just not enough information. For these weaker notions, it can be shown that maximal lotteries actually satisfies these conditions. There's also another variant of strategy proofness that was shown by some French authors, where they show that whenever there's a Condorcet winner, maximal lotteries are strategy proof, and which, if you just consider the domain where Condorcet winners always exist, is not that surprising. But for maximal lotteries, it's even the case that you cannot manipulate a way to a different preference profile in which there is no Condorcet winner. So that has been shown in a paper. So there are some weakenings of strategy proofness which are actually satisfied by maximal lotteries. Another interesting point, I think, is the degree of randomization, because especially when you talk to political scientists, so some of them are really concerned about using any randomized method at all. And therefore, an interesting question is how much randomization does maximal lotteries actually entail? And it turns out that the degree of randomization is surprisingly low, because for most preference profiles, for most realistic preference profiles, it's very likely that Condorcet winners exist. And even for those preference profiles for which we don't have Condorcet winners, maximal lotteries just randomizes over very few alternatives. We have studied this in detail by looking at a couple of various distributions of preference profiles, such as impartial culture, impartial anonymous culture, and some spatial models. And then we studied the support size and also the Shannon entropy of maximal lotteries, and that was rather low. And finally, this is an ongoing project by Florian and myself. So we are currently looking at a dynamic earn process which converges towards maximal lotteries. And here the idea is that we don't want to have a central authority which just takes a preference profile as an input and then computes the maximal lottery, but rather a dynamic process where you just take balls from an urn and replace them with other balls, and then naturally maximal lotteries evolve over time rather than being computed by a central authority. And finally, let me just mention this website here mentioned down here, voting.ml, where ML is not machine learning, it's maximal lotteries in this case. And this website just allows you to play around with maximal lotteries. So if you got interested, you can just open this website and compute it for some preference profiles and see what maximal lotteries is doing. Thanks very much. Okay, so I think you were referring to the first statement that I had on this slide, so where we take errors in possibility and turn it into a characterization of maximal lotteries. So in contrast to what I presented here, this actually uses preferences over lotteries, and what we do there is that we just extend the space of alternatives to the space of all lotteries, and then Pareto dominance is just defined as usually. And independence of irrelevant alternatives is just defined by looking at feasible subsets that are convex combinations of alternatives. So we are looking at its subvertices, essentially, between different alternatives. And whenever the preferences between alternatives that are not contained in this polytope change, then everything in this polytope should also not change as well. And for this setting, so maybe one major piece of information that is useful here is that we are not using von Neumann-Morgenstern utilities in that paper, but we use a generalization of von Neumann-Morgenstern utilities called skew-symmetric bilinear utilities, which was proposed by Fishburne. And in that generalized setting, we can get this complete characterization, whereas using von Neumann-Morgenstern utilities, we only get positive results using dichotomous preferences. So for dichotomous preferences, approval voting does the job. And approval voting is just a special case of maximal lotteries for dichotomous preferences. But for the more general case, we need these skew-symmetric bilinear functions. Okay, that's a good point. So so in the statement I just said we are using these two consistency conditions, and then I said I brushed over some technical details, and there's one condition which it's not Pareto optimality, it's much weaker than that. So we have one statement which says if there's only one voter and two alternatives, and this voter prefers A to B, then A should get probability. Then actually it's even weaker than that. We just say that B should not get probability 1. So that's really probably the weakest thing you could think of. But we have some condition like this because otherwise, as you said, of course, it wouldn't work. Yeah.
Great, thanks. Thanks, Felix. And I would like to thank Annie, Peter, and Felix for 3 wonderful talks. And thank you all.